3 meals a day, breakfast at 7 o'clock, lunch at noon, dinner at 6 o'clock. A schedule that was never based on physiology. It was based on factory shifts, school bells, and the industrial clock that organized society around meal times derived from work patterns rather than from anything the gut requires. You followed the schedule or you followed the newer advice. Eat smaller meals more frequently, every 2 to 3 hours, to keep the metabolism running. Your gut was never consulted about either plan. And between meals, only between meals, the small intestine runs a cleaning wave that sweeps its entire 6 meters length, pushing debris, dead epithelial cells, mucus, and bacteria toward the colon. The wave needs 90 minutes to complete one cycle. It resets to zero the moment food arrives. The cleaning system that maintains bacterial balance and clears residual material from the intestinal surface operates exclusively during fasting and shuts down completely the instant digestion begins. If you eat every 2 to 3 hours, as the advice repeated for decades recommended, you eliminate every gap long enough for the wave to finish. The gut that is always digesting is a gut that is never cleaned. The question was never how many meals to eat. The question was whether the gaps between them are long enough for the wave to complete, and the answer depends on a cleaning system you have almost certainly never been told exists. What is this cleaning system, and why have you never heard of it? A cyclical electromechanical pattern in the gut wall that activates only during fasting was first identified in the American Journal of Physiology in 1969. Shushevsky named it the Migrating Motor Complex, 4 phases cycling over 90 to 120 minutes, each phase performing a specific function in the cleaning sequence. Phase 1, quiescence, approximately 40 to 60 minutes of electrical silence. The smooth muscle of the small intestine is quiet, minimal contractions. The gut rests between cleaning cycles, conserving energy while the system prepares for the next sweep. Phase 2, irregular contractions, approximately 30 to 45 minutes of increasing contraction frequency and amplitude. Bile and digestive secretions flow into the intestinal lumen. The system builds toward the sweep, each contraction slightly stronger than the last. The wave gathering force across half an hour of progressive recruitment. Phase 3, the sweep itself. Approximately 5 to 15 minutes of the most forceful coordinated contraction the small intestine produces outside active digestion. A peristaltic wave propagates from the stomach through the entire length of the small intestine, approximately 6 meters at 5 to 10 centimeters per minute. The wave pushes everything in its path. Undigested food particles too large for enzymatic breakdown. Dead epithelial cells shed from the intestinal lining during its continuous 3 to 5 day turnover cycle. Mucus that has accumulated on the surface, and bacteria that have colonized the small intestinal environment during the preceding hours. Phase 3 is the housekeeper. Hallway must be empty for the sweep to run. Each person entering the hallway sends the housekeeper back to the starting position. Each snack arriving in the gut suppresses the motilin that was building toward the next phase 3 contraction, resetting the hormonal clock to zero. The housekeeper does not pause and resume. The housekeeper restarts from the beginning of phase 1, and the full 90 to 120 minute cycle must complete again from scratch before the next sweep can run. Phase 4, brief transition. A few minutes of declining contraction amplitude as the wave reaches the terminal ileum and the peristaltic force dissipates. The cycle either restarts at phase 1, beginning another 90 to 120 minute progression toward the next sweep, or is interrupted by food intake, which terminates the entire sequence through motilin suppression and switches the gut from cleaning mode to digestion mode. The transition between modes is absolute. The gut performs one function or the other, determined entirely by the presence or absence of food in the stomach. How long does the complete cycle take? 90 to 120 minutes for one complete cycle. Subsequent studies confirmed the cycle duration across multiple measurement techniques. The gut needs the full sweep window of uninterrupted fasting to complete one full sweep from stomach to terminal ileum. Any caloric food intake resets the cycle to phase 1. The clock restarts only after the stomach empties, typically 3 to 5 hours after the meal that interrupted it, with the duration depending on macronutrient composition. Carbohydrate-dominant meals empty fastest, typically 2 to 3 hours, because simple carbohydrates require minimal mechanical breakdown and pass through the pylorus into the duodenum with relatively low resistance. Protein-rich meals empty at an intermediate rate, 3 to 4 hours, because protein digestion requires more gastric acid exposure and mechanical churning before the particles are small enough to pass the pylorus. Fat-rich meals empty slowest, 4 to 5 hours or longer, because fat triggers the release of cholecystokinin from the duodenal lining, and cholecystokinin contracts the pyloric sphincter, deliberately slowing gastric emptying to match the rate at which bile and pancreatic lipase can process the fat downstream. The macronutrient composition of dinner directly determines how long the stomach takes to empty, which determines when the overnight fasting window begins, which determines how many complete sweeps the gut runs before breakfast. What happens when the wave cannot finish? If you eat breakfast at 7 o'clock, snack at 9:30, eat lunch at noon, snack at 2:30, eat dinner at 6 o'clock, and snack at 8:30, you have given the gut zero fasting windows long enough for the migrating motor complex to complete during waking hours. The cleaning wave starts after each meal's digestion, builds through phase 1 and phase 2 across an hour or more, and is interrupted by the next food intake before phase 3 can run. The sweep never reaches the end of the small intestine. The housekeeper starts down the hallway, someone enters, the housekeeper returns to the starting position, begins again, someone else enters. The hallway is never cleared, consequences build in the space the wave was supposed to clear. The small intestine normally maintains a low bacterial population, approximately 1,000 to 10,000 colony-forming units per milliliter in the jejunum, compared to the colon at approximately 100 billion to 1 trillion colony-forming units per milliliter. The difference is a factor of approximately 100 million, 8 orders of magnitude, separating the bacterial density of the small intestine from the bacterial density of the colon. The migrating motor complex maintains this differential by regularly sweeping bacteria from the small intestine into the colon where they belong. Without the sweep, bacterial populations in the small intestine climb. Bacteria that should have been pushed into the colon remain in the jejunum and ileum, establishing populations in a territory the body designed for absorption rather than fermentation. The small intestine is architecturally optimized for nutrient absorption. Its villi and microvilli create an enormous surface area across which amino acids, simple sugars, fatty acids, vitamins, and minerals cross into the bloodstream. Bacteria colonizing this surface compete with the enterocytes for the nutrients passing through, consuming substrate the body intended to absorb, and producing metabolic byproducts the small intestine was never designed to handle. The bacteria ferment carbohydrates that arrive partially digested from the stomach and duodenum. The fermentation produces hydrogen and methane gas through bacterial metabolism of the carbohydrate substrates. Hydrogen is produced by nearly all fermenting bacteria. Methane is produced by a subset called methanogens that convert hydrogen and carbon dioxide into methane through a separate metabolic pathway. Both gases accumulate in a location that is architecturally narrow, approximately 3 centimeters in diameter, and highly innervated with sensory neurons that register distension as discomfort. A volume of gas that the colon at 5 to 6 centimeters in diameter and with a wall designed to accommodate gas production from normal colonic fermentation would absorb, without sensation, produces measurable distension and pain in the smaller diameter small intestine, because the smaller tube stretches proportionally more from the same gas volume. The bloating that arrives 30 to 60 minutes after eating, the distension that makes the waistband tight by afternoon. The gas that you attributed to specific foods, lactose, gluten, cruciferous vegetables, may have been partially caused by bacteria fermenting in the wrong location. The metabolic consequences extend beyond gas production. Bacteria in the small intestine deconjugate bile acids before those bile acids can perform their primary function, emulsifying dietary fat for absorption. Conjugated bile acids are the detergent molecules the liver produces to break dietary fat into micelles, small enough for the intestinal wall to absorb. When bacteria cleave the conjugation bond, the deconjugated bile acid loses its emulsifying capacity. Fat passes through the small intestine unabsorbed, producing the fatty, pale, malodorous stool clinicians recognize as steatorrhea. Additionally, bacteria in the small intestine consume carbohydrate substrate before the enterocyte brush border enzymes can break it down for absorption. The bacteria eat the sugar before you can. The combination of fat malabsorption from deconjugated bile and carbohydrate malabsorption from bacterial consumption produces nutritional consequences that the bloating alone does not reveal. Impaired cleaning wave function is associated with small intestinal bacterial overgrowth, an association Pimentel and colleagues established in the American Journal of Gastroenterology. Whether meal pattern-induced interruption alone produces clinically significant overgrowth in healthy individuals has not been isolated in a controlled trial, comparing identical diets with different meal frequencies while measuring small intestinal bacterial counts. The study has not been conducted. Many people eat frequently for years without developing diagnosed overgrowth, which may reflect individual variation in baseline motility strength, gastric acid production that limits bacterial survival in the upper intestine, and immune surveillance along the intestinal wall. The association between impaired sweeping and bacterial migration is established through clinical evidence in patients with documented motility disorders. The threshold at which interrupted cleaning produces symptomatic consequences varies between individuals. I traced my own afternoon bloating to the snacking pattern the week I learned the cleaning wave existed. The mid-morning handful of almonds, the afternoon energy bar, the post-dinner crackers, each one arriving before the previous meal's digestion had completed and the cleaning cycle had begun. Every gap eliminated, every sweep interrupted before phase 3 could run. The bloating I had attributed to food sensitivity was timing sensitivity, the consequence of a cleaning system that could not complete its cycle because I never gave it a gap long enough to finish. Now, the wave runs in 4 phases over 90 minutes and sweeps the small intestine from top to bottom. The consequences of interruption accumulate in the space the wave was supposed to clear. But how does the gut generate a coordinated wave across 6 meters of smooth muscle in the first place? The answer runs through a pacemaker system the gut shares with the heart, and a hormone that only appears during fasting. How does the gut know when to sweep? Pacemaker cells, called interstitial cells of Cajal, sit in the myenteric plexus, the layer of neural tissue sandwiched between the circular and longitudinal, smooth muscle coats of the intestinal wall. Each pacemaker cell connects to its neighboring smooth muscle cells through gap junctions, protein channels that allow the electrical slow wave to pass directly from the pacemaker into the contractile tissue without requiring a neurotransmitter or a synapse. The coupling is direct. The pacemaker depolarizes. The current flows through the gap junction into the adjacent smooth muscle cell, and the muscle cell depolarizes in turn. The mechanism is analogous to the cardiac pacemaker cells in the sinoatrial node, which also generate rhythmic depolarizations and transmit them through gap junctions to the surrounding myocardium. The difference is molecular. Cardiac pacemaker cells use funny channels that open at hyperpolarized voltages to initiate each beat, while intestinal pacemaker cells use calcium-activated chloride channels to generate each slow wave cycle. Different channels, same principle. A specialized cell that generates a rhythm the surrounding muscle follows. Takahashi described their role in the Journal of Smooth Muscle Research. These cells depolarize the smooth muscle membrane at approximately 12 cycles per minute in the duodenum, declining to approximately 8 cycles per minute in the ileum. The frequency gradient along the gut's length ensures that contractions always propagate in the oral to anal direction, the higher frequency upstream driving the wave distally through the same physics that makes a faster metronome entrain a slower one. The slow waves set the maximum contraction frequency, but do not produce contractions on their own. Contractions occur only when the slow wave amplitude exceeds the threshold for opening L-type calcium channels in the adjacent smooth muscle cells. When the threshold is crossed, calcium ions flood through the channels into the muscle cell, triggering the contraction. When the threshold is not crossed, the slow wave passes without contraction. The pacemaker ticks continuously, 12 times per minute in the upper small intestine, 8 times per minute in the lower, a gradient that ensures the electrical rhythm always runs faster upstream than downstream, which is why peristaltic waves always propagate in the oral to anal direction, regardless of the intestinal contents or the type of contraction. The gradient is the same physics that makes a faster oscillator entrain a slower one. The upstream segment contracts first, the downstream segment follows, and the wave moves distally through the frequency difference the pacemaker gradient establishes. Whether each tick produces a muscular squeeze depends on whether the signal crosses the threshold that opens the L-type calcium channels in the adjacent smooth muscle. During phase 3, the hormone motilin amplifies the signal above the contraction threshold. Motilin, released from specialized cells in the duodenal lining during fasting, amplifies the slow wave amplitude above the contraction threshold across sequential intestinal segments. Van Trappen and colleagues confirmed this mechanism in the Journal of Clinical Investigation. Each segment contracts after the one above it. The coordinated peristaltic sweep propagates from the stomach through the entire small intestine, each contraction pushing the contents distally into the next segment. The wave advancing at 5 to 10 centimeters per minute across the full intestinal length. Now, the guiding mechanism that makes cleaning and digestion mutually exclusive. Eating suppresses motilin release through a hormonal feedback mechanism. When food arrives in the stomach, the duodenal endocrine cells that produce motilin receive inhibitory signals from cholecystokinin and gastric inhibitory peptide, both released in response to the nutrient content of the arriving meal. The inhibitory signals silence motilin secretion within minutes of food reaching the duodenum. Without motilin, the slow wave amplitude stays below the contraction threshold. Phase 3 cannot occur. The sweep cannot run. The architecture ensures that cleaning and digestion are mutually exclusive by hormonal design. The gut does one or the other, determined by the presence or absence of food in the stomach. If you eat continuously, motilin stays suppressed continuously, and the cleaning wave stays silenced for every waking hour. The suppression is hormonal, not neural. The gut does not decide to stop cleaning. The hormonal architecture prevents cleaning from being biochemically possible during digestion. Motilin levels cycle during fasting with a periodicity that matches the cleaning wave cycle, peaking approximately every 90 to 120 minutes. Each peak triggering a phase 3 sweep. During feeding, the motilin peaks disappear from the blood entirely. The hormone is not merely reduced, it is absent. The cleaning wave cannot run because the molecule that triggers it is not being produced. Does the number of meals matter, or does the physics prescribe something else? 3 meal patterns tested against the cleaning wave cycle duration requirement. 3 meals with no snacking, breakfast at 7 o'clock, lunch at noon, dinner at 6 o'clock. The stomach empties approximately 3 to 5 hours after each meal, depending on meal composition and size. After breakfast, the stomach empties by approximately 1000 to 1100 in the morning, 1 to 2 hours of fasting before lunch, possibly one partial cycle, enough for phase 1 and phase 2, but likely too short for phase 3 to complete. After lunch, the stomach empties by approximately 3 to 4 in the afternoon, 2 to 3 hours before dinner, one complete cycle if the gap reaches 90 minutes of fasting, one full sweep through the small intestine. After dinner, the stomach empties by approximately 9 to 10 in the evening. 9 to 10 hours of uninterrupted overnight fasting before breakfast. 5 to 6 complete cycles. Total, approximately 6 to 7 cleaning cycles per day. 6 to 7 complete sweeps through the 6-meter length of the small intestine every 24 hours. Adequate maintenance by every clinical measure of gut motility, bacterial population control, and intestinal surface clearance. The 3-meal pattern, derived from factory schedules and school timetables, accidentally provides the fasting architecture the motility cycle requires. The number was never physiologically prescribed. The gaps the number creates happen to match the physics. 3 meals with snacking. Breakfast at 7 o'clock, snack at 9:30, lunch at noon, snack at 2:30, dinner at 6 o'clock, snack at 8:30. Every daytime gap eliminated. The stomach never empties long enough between inputs for fasting to begin. 0 completed daytime cycles remain, approximately 4 to 5, depending on when the evening snacks completes. cleaning capacity reduced by roughly a third compared to the no snacking pattern. 6 small meals, eating every 2 to 3 hours from 7 o'clock in the morning through 9 o'clock in the evening. Gaps between meals after stomach emptying are 30 to 90 minutes. Too short for the fasting sequence to reach phase 3 in any daytime window. 0 completed cycles during waking hours. 14 hours of continuous digestion with no maintenance interval. The gut relies entirely on the overnight fast for its fasting sequence. And the overnight fast begins only after the final meal's digestion completes, which may not occur until midnight or later, depending on the composition of the last meal. Well, the physics does not prescribe a meal number, it prescribes gaps. Fasting windows long enough for the migrating motor complex to complete at least one full cycle. 3 meals with no snacking provides those gaps. 6 small meals eliminates them. The meal count was never the variable. The silence between the meals was the variable the peristaltic program depended on. Meal pattern determines the number of completed sweeps. 3 meals with no snacking, adequate gaps. 6 small meals, 0 daytime cycles. But the largest variable in the daily cleaning count has nothing to do with the number of meals. It is the length of the overnight fast, and the length of the overnight fast is controlled by a single decision: when dinner ends. Circadian glucose research shows the same meal producing a higher glucose peak at 8 o'clock in the evening than at noon. Dinner timing carries a second dimension beyond the glucose curve. Earlier dinner also means a longer overnight fasting window, and a longer overnight fast means more complete MMC cycles before breakfast. Dinner at 6 o'clock, breakfast at 7 o'clock the next morning, 13-hour overnight fast. The stomach empties by approximately 9 o'clock in the evening. 10 hours of uninterrupted fasting during which the motility sequence cycles continuously. 5 to 6 complete sweeps through the small intestine. Dinner at 9 o'clock, breakfast at 7 o'clock the next morning. 10-hour overnight fast. The stomach empties by approximately midnight. 7 hours of cycling, 3 to 4 sweeps. Moving dinner 1 hour earlier adds approximately 1 additional complete cycle per night. Across a year, that arithmetic suggests roughly 365 additional sweeps. The exact count depends on individual gastric emptying rates, meal composition, and overnight motility variation. The arithmetic is approximate, but the direction is consistent across every individual. Earlier dinner extends the overnight cleaning window, and the overnight cleaning window is where the majority of the gut's daily maintenance occurs. The difference between a 6 o'clock dinner and a 9 o'clock dinner landed differently once the overnight arithmetic reached specific numbers. 2 fewer motility cycles per night, roughly 700 fewer sweeps per year, a maintenance deficit the gut accumulated silently across every year the late dinner persisted. The overnight fast is the gut's primary cleaning window, and the morning routine that follows it often begins with something that amplifies the wave. The overnight fast was running. Why does the morning coffee send you to the bathroom? Caffeine stimulates motilin release from the enterochromaffin cells in the duodenal lining. The morning coffee, arriving in a gut that has been fasting overnight for 10 or more hours, amplifies the phase 3 contractions that were already cycling through the small intestine during the overnight fast. The caffeine boosts the circulating motilin level above the baseline fasting concentration, pushing the contraction amplitude higher and the transit speed faster than the overnight motility cycle would produce on its own. The urgency to use the bathroom within 20 to 30 minutes of morning coffee is phase 3, being pharmacologically amplified by a substance that targets the same hormonal pathway the gut uses to trigger its own sweep. The coffee did not create the wave. It amplified a wave. The overnight fast was already running, and the amplification pushes material through the ileocecal valve into the colon, triggering the defecation reflex that follows. Pharmacologically, the system is specific enough to have a clinical application. Erythromycin, the antibiotic, is a motilin receptor agonist. It binds the same receptor motilin binds and triggers phase 3 contractions directly. Gastroenterologists prescribe erythromycin off-label as a prokinetic agent specifically because it activates the fasting sequence through the motilin receptor. The gut's cleaning system is pharmacologically accessible because it runs on a specific hormone with a specific receptor, And both caffeine and erythromycin access that receptor through different pharmacological mechanisms. Caffeine stimulates motilin release from the enterochromaffin cells, increasing the circulating hormone level that then binds the motilin receptor on the smooth muscle. Erythromycin binds the motilin receptor directly, mimicking the hormone without requiring its release. The clinical application confirms the basic science. The peristaltic program runs on a receptor system specific enough to be targeted by a drug, which means the wave is a hormonally gated, receptor-mediated, pharmacologically accessible cleaning program. The gut runs on a predictable schedule whenever fasting provides the conditions it requires. And then there is one more piece of this physics you already experience. You have heard the MMC cycle your entire life, borborygme, the stomach rumbling that arrives 3 to 4 hours after a meal, the sound that echoes across quiet rooms and silent meetings. The sound is the motility sequence, phase 2 and phase 3 contractions propagating through a gut containing air and residual fluid, but no food bolus. The air-fluid interface produces the audible gurgling as the wave compresses gas pockets along the intestinal length. The sound propagates through the abdominal wall because the air column within the intestine acts as an acoustic waveguide. The wave compresses a pocket of gas. The compressed gas transmits the pressure pulse along the tube, and the intestinal wall vibrates against the surrounding tissue and the abdominal wall at a frequency the human ear can detect. The volume is proportional to the amount of air present, the force of the contraction, and the emptiness of the gut. A gut containing food absorbs the sound into the food bolus. A gut containing only air and residual fluid amplifies the sound because the air-fluid interface generates stronger acoustic reflections than food against wall contact. The emptier the gut, the louder the rumble, because an empty tube with gas pockets generates stronger acoustic resonance than a tube dampened by food material. The louder the rumble, the more effectively the fasting sequence is running. A completely silent gut during the hours between meals may indicate that the motility cycle has not activated either because digestion from the previous meal is still running or because the motilin release that triggers phase 3 has not yet peaked. The rumbling is the audible confirmation that the gut has entered its maintenance phase and the sweep is propagating through the intestinal length. Borborygme is the motility cycle you can hear. The embarrassment in a quiet room is the sound of the gut performing its maintenance. The gut that rumbles between meals is a gut whose fasting sequence is running. The gut that stays silent all day. The gut that never rumbles because it never reaches the fasting state where the wave activates may be a gut that has not cleaned since the overnight fast ended. 3 meals a day was never a physiological prescription. It was an industrial schedule that happened to provide the fasting gaps the gut's cleaning system requires. The gut does not count meals. It counts the gaps between them because the wave that maintains the bacterial differential sweeps the debris and keeps the small intestine clear runs only when the gut is empty. The wave needs the full cycle duration. It resets to 0 when food arrives. 3 gaps per day gave the wave time to finish. 0 gaps gave the wave nothing to work with. The number of meals was never the question. The length of the silence between them was the answer the gut was waiting for.